Okay, so yeah, last time, I guess we can pull up Vivado here. Okay, get rid of putty here. Okay, so last time we looked at building hardware with a processor and some simple stuff connected to the bus. Okay. So what we're going to do this time is we're going to look at a different way to create hardware. Okay, and this is using a technology called high-level synthesis. And what that does is it takes, rather than having to write Verilog, we can write C code and it will create Verilog for us. Okay, why might we? You don't have to look at this. This is nothing up here. Why might we want to do that? Why would you like to create your hardware from C code or something like that? Yeah.
Most everyone knows.
Okay, so lots of people know it. Okay, I agree. Maybe it's not the best language to describe hardware with. It's actually a pretty bad language to describe hardware with. But it's called that everyone knows. So if you are a company that wants to make dollars, you want people to use your tool, so you pick a language that people know. Okay. Yeah.
Just an idea that I had is maybe like if you're trying to model a sequential circuit, like some of that behavior could be modeled in code that's compiled line by line.
Okay. So this is good. You've identified your already your brain's going, well, wait a second. Software is sequential and a circuit is not sequential. So maybe if you want to make some sequential circuit for some reason. So you're right. We generally want to do stuff parallel, and that's not what C does, but we're going to make it do it anyway. Okay. So I don't know what else. I mean, is it easier to write one or the other? Okay. Yeah.
If you already have like a complex algorithm written in C, if you're using it, and you might want to run that through GA, it might run faster.
Okay.
Algorithm. It's something you could do, and you save a lot of development time and money that it would take to maybe convert that entire thing into Verilog and optimize it for that. Well, for us to do it, it may not be as optimized.
Okay. Okay. So even if it's not the best hardware, it might be faster than our software. Okay. So let's talk about the complexity side. So let's say, so we're going to do really simple algorithms here. Let's say you've got some numbers in memory, okay? And you want to add them up. Okay, let's say 100 numbers sequentially stored in memory somewhere. And you want to write some implementation that retrieves them from memory and sums them. How hard is that to do in C code with a processor? Not hard. Okay. So like you declare an array, a little for loop, like 3 lines. Okay. So what about Verilog? Could you, I mean, we don't, it's different than what we ask you to do in 220. Could you make a Verilog circuit that does that? Let's say your numbers are stored in a VRAM on the chip. Okay. So you got 100 numbers in a VRAM, and you would like to output the sum of them out of your module, out of some output on your module. Could you make that Verilog? What would it look like? Yeah.
I guess you have a register where you write the beginning address of a set of numbers, and then another one where you write like how many you want to take from it.
Okay.
And then you have some like iterative circuit that like increments that counter while reading from memory and puts it through an adder each time.
Okay. Okay. So you got an adder. Now, what about reading from memory? We never have done that in 220. Okay. Have you seen the signals that go into a memory before? What do you have in general? An address, a read or a write signal that you feed in. And if we're writing, then a data signal goes in. If we're reading, the data signal comes out. So that's at minimum. So at minimum, we have to, and okay, I mean, when does the data come out of the memory? Is it just like instantly when we put the address in, magically the data? Pardon?
You need a clock.
Okay, so there's a clock, and it depends on the memory. Okay, if it's a simple memory like a VRAM, you might just know I need to wait till the next clock cycle. Okay, if it's more complicated like a DRAM, you might have to wait some arbitrary number of cycles before the data is there. But either way, you're going to have to build a state machine that feeds an address and a read signal in. You're going to have to wait a little bit for the data to come back. You're then going to have to sum it with an adder and a register. Then you're going to have to increment the address. Then you're going to have a comparator that checks if you've reached the end or not. Okay, and you're going to be worrying about clock cycles through all of this and making a state machine. So I hope you see, just to do the same thing in Verilog, there's a lot more details. So when we write C code, do we worry about what clock cycle things happen at? No, we just hide all that stuff, right? And so there's a lot of motivations to write stuff at like the C level because it's easier and faster to write it, okay? And that means a lot. That means dollars. If your developer spends less time working on it, then that's good. It's cheaper. Maybe we could write some Verilog that's a little more efficient and a little faster. But is it worth all the extra time to put into it? Okay, so what else? What other advantages? We talked about, I mean, the performance, okay, how much time it takes to develop. What else would a engineering team care about when choosing different tools to use? What is the cycle we talked about? We design something, and then what do we have to do? Test it, okay? So, I don't know, if you want to write, you're in test code for Verilog. We've given you test code, right? In 220, we gave you test benches. Okay. So say you want to add up these 100 numbers and check that the number is right. Would you rather write the test code in C or Verilog? C. Okay. What might it be in C? You might know the answer, and you might just say, check the answer. And Verilog is test bench. Oh, I got to put in my clock. I got to reset it, unreset it. And then I need to like feed all the signals I'm interested in to some waveform and then write some script in System Verilog or something. Okay. So the other kind of piece of the puzzle is that it makes it a lot nicer to test our code, that our code is correct when writing it kind of at the software level. And we can just run it as software. Okay. So let me show you. You can still see what's going on here. Okay. Okay, so this is the code that I want to hardware accelerate. Okay, and generally the way that we hardware accelerate stuff is we have a function in C code that we want to turn into hardware. The function is not main, okay, it's some other function, not called main, okay, and it can have arguments, okay. What would the arguments mean? Why would you want? What's the analogy in hardware to software function arguments? Like ports on your module, right? Okay, inputs and outputs, ports. Okay. So this function, it has some memory inside of it. I'm kind of talking more in hardware lingo here than software, but in the software world, right, there's a automatic variable here, an array of 1,000 integers. Okay. And basically what this function does, I don't know why you'd want such a thing, but it counts how many times a certain number, the input, occurs in this list. Okay. So here is what I have. Please don't be thrown off by this. If you didn't know, in C, you can label your loops if you would like to name things and give them cute names. Mine's pretty boring. It's called main loop, but the software likes it when our loops are named because we're going to apply optimizations to them. So I've got a for loop, goes through 1,000 things. Okay, it checks if this index in the array matches my input, and if so, I increase it. Otherwise, I increase it by 0. That's kind of weird. Okay, this is some leftover experimentation from our class, I think. And then I return the number out of the function. Okay, so let's get the tool running here. So the tool is called Vitis HLS. Okay, right? We used normal Vitis before to do software running on the ARM processor. This is Vitis HLS. Okay, so when we open this up, we're gonna create a new project. Okay, and let's see, project name. Where is it gonna put this thing? Let's go throw it in temp again. Okay, so we'll just call this bootcamp demo. Okay, and so now I know, I'm sorry, it's really small, but basically it wants us to add design files. Okay, on the next tab, we're going to add test bench files, and again, this is kind of a weird name. You think in the hardware world, we call them test benches. In software, we don't really call them test benches. We just call it test code or test functions or something, right? So, okay, before I continue, I want to go back to my code and show you. Okay, so I had this function, but I also have a test function, okay? And in my test function, I'm going to check how many times the number 13 occurs. Okay. And personally, I know how many times it occurs because I've checked myself, okay? And I know that it occurs 12 times, okay? So this is my test code. Again, it's way simpler than a Verilog test bench, but it checks that this function works correctly, okay? It's not super rigorous, but it checks for one input, okay? So anyway, going back, I'm going to add, go back. I'm going to add design files. So these are C code files that are going to turn into hardware. So I'm going to hit add files. Sorry, let me just go back and make sure that we're going to create this in a subfolder. To make sure it doesn't mess with those. Okay. So we're going to add this. And so really just count.c is the only file that I'm turning into hardware. And then I need to pick which is my top function. So you can still do things like function calls. Okay. So let me ask you this. I mean, pretend yourself you're designing this technology. You don't know how it works yet. How would you do a function call in hardware? What does that even mean? Okay, well, how would you make a function? Like you talked about like sequential code. How do you do sequential steps in hardware? Like a finite set of steps. A finite set of steps, yeah. Yeah, a finite state machine, right? Okay, so that's when we want to do things in a sequence and have conditionals and things like that. Okay. So you think like if you wanted to basically go run some other sequential set of steps, you might have just another module that also has a state machine, and your kind of parent state machine starts that one and waits for it to finish, and then it continues on. So that's really what happens in hardware when all this stuff gets built. But okay, so we have to choose which is our top function, and thankfully we only have one function, count occurrences. There's not a lot of agency here. Okay, and then we test bench files. I'm going to choose my count test. Okay, and then it says, hey, choose a clock period. this is a really neat thing about high-level synthesis is, right, there's no notion of clocks in C code. So what it's going to try and do is, I don't know, if you kind of think back to 330, we don't talk about this as much in the hardware world. So I'll refer back to 330 where we talk about, oh, how much work you can do in each state in your state machine and software before you like miss interrupts, okay? It's the same analogy in hardware. You can only do so much work between clock ticks. And if you try and put too much combinational logic there, okay, then you're going to violate the clock period. So what's neat is that this tool is going to make the Verilog for us. We're going to tell it what part we're using and what frequency we want to meet, and it's going to build the state machine such that it will try and predict how much work it can get done in each clock cycle, but still meet the frequency target. So that's really cool. You probably don't, even after my unclear explanation, you probably don't appreciate how cool that is, in the sense that if I wanted to come back and target a different clock period, I could just come here and change it and rerun it. If I said, oh, go make your Verilog run at a clock that's twice as fast, you'd have to start like ripping things apart and adding in new states and new flip-flops and splitting stuff up between different states in your state machine and things like that. And you have to restructure all of your code. You don't have to do that here. You just change a drop down. So it's kind of neat when things are auto-generated for you. But we're going to target 100 megahertz clock. 100 megahertz equals 10 nanoseconds. Okay. And the part, well, we might as well at least pick our normal part from the board I was using. Okay. Okay. Okay, so if we look up here, again, I know, I'm sorry, it's small. There's sources and test bench, and we can look at our file. Okay, this is the same one that I already opened VS Code, and in VS Code I can make it bigger. So, okay, so what we're going to do is we're going to check that it works correctly. Okay, and so what we're going to do is we're just going to run it in software. Okay, so I can go up to this little play button, and I can say, C simulation. What a weird word. Again, this is hardware world. We're going to simulate it, but it's just running C code. Okay, so it's going to compile it with GCC, and it'll run it. Okay, I could have gone into the command line and compiled it with GCC and run it, but it's kind of nice. It just does it for us. So there's also some special libraries and things that come with the tool. Whereas if you tried to just go to your command line and compile at GCC, it wouldn't hook into all these existing libraries. So often you want to come here and do this. But hey, look, it says csim will launch GCC as the compiler. Okay. Okay, so hey, look. Says there are 12 occurrences of 13 in the array. Okay, finish with 0 errors. Okay. I could change this if I want. I could say, oh, no, please check that there are 14 of them. Okay, and I can run this again, and I hope it runs faster this time. No, still slow. But here you can essentially verify that you've written the C code correctly. Okay, and you see there's an error. It's got this like tickle call stack, but either way, they'll say, hey, you know, this thing returned a non-zero value, and there's an error, so it doesn't work here. Okay, there you go. There's assertion failed. Okay, so I'll go back and switch that back. Okay, so far we're still just like living in the software world, but we're gonna take the bridge and make some hardware. Any questions at this point? Okay, so here we go. We are gonna run C synthesis. Okay, and I promise it will make Verilog much faster than you could make Verilog. And it's not like waiting for Vivado. My computer runs in like slow mode when it's not plugged in. No, it's on best performance. Okay. Oh, sorry, I just had to scroll. It's already done. Okay, so when it finishes, it does something. It puts some stuff up here. Yeah, it's kind of hard to see, so I'll read to you. One, okay. So let's see. We've got some general information. There's nothing in there we really care about. Okay. Timing estimate. It says our target was 10 nanoseconds. It says, hey, that's pretty easy. I think this will run with a 6.4 nanosecond clock. Okay. So I don't know. What's that? 170 megahertz or something? Yeah, something like that. With some uncertainty of 2.7 nanoseconds. Why would there be uncertainty? Why wouldn't it just know? It's Xilinx. It's their part. Yeah.
Because not all transistors are equal.
Okay. Okay.
Bad answer, but
That's true, but even there are things that cause even bigger problems than that.
it could be different parts are different voltages. That might play into it.
Okay, so at this point, it could create a net list essentially. Okay, but still, why might you not know how fast your net list is going to run targeting a part? Yeah.
Because you haven't ran like place and route on it.
Yeah, it hasn't actually decided where it's going to put it on the chip. Okay, so it's not actually part of the design, so you don't know how far apart gates are going to be. And you don't know if the routing is going to go directly or go winding around. And if you put this in a design with lots of other stuff and it's really congested, then it's harder to find direct routing paths. And so until you actually place and route it in Vivado and wait the time to do that, you don't really know how long those paths are and how fast you can run. Okay. So it's just a guess at this point. Okay, so what else do we want to see? So we have a function called count occurrences. Inside of it is a loop. You remember we labeled it. We labeled it main loop. But this function, it knows it's going to take 1,002 cycles to run. Okay. So there were 1,000 iterations in our loop. So you can say, well, okay, each iteration loop is going to take one cycle, and then a little bit of extra. Okay. So yes, sure enough, the main loop. Let's see, the whole loop is going to take 1,000 cycles to run, but each, we've got two numbers here: iteration latency and interval. Okay, so it actually takes 2 cycles to do each iteration of the loop. Okay, because we have to feed the address into the memory. Remember, this is a big array. We're not adding them up like my earlier example, but we're still doing the same thing. We're going through and looking at all the entries and counting them. Okay, so we have to basically feed an address in, wait for the data to come out the next cycle, and check it. So it takes 2 cycles. So magically, if we do something that takes 2 cycles 1,000 times, it only takes 1,000 cycles. Who wants to explain that math for me? How is that? If it took you 2 states of your state machine to get something out of this loop, and you got to do it 1,000 times, shouldn't it take 2,000 cycles? If I say I'm your manager and I'm paying you, please make this faster. How would you make it faster? I heard the word. Someone said it. Yeah, pipeline. Okay, what does pipeline mean?
You can, get things done, like, kind of parallel, but it's like,
Okay. Overlap?
overlap, yeah.
Overlapped, yeah. Okay, so pipelining is about overlapping operation. So at time 0, I feed in address 0, and at time 1, oops, I missed the board. Okay, so maybe every iteration of the loop takes 2 cycles. One where I have to, let's say, provide address into the memory, and then this one where essentially the data comes out of the memory. Okay? But the way the memories are built is they're built to be pipelined. There's a register inside. You don't have to wait for the data to come out. You don't have to do this. Okay? So, right, we're going to do this 1,000 iterations of the loop. We don't have to do that. You can actually build your circuit like this. Okay? So while you're getting the data out from the last one, you're feeding in the address for the next one. Okay? And this is why these tools are really smart and do a better job than you. But you can do this. And if you are tasked with writing high-performance Verilog, we never do this in 220. We never ask you how many cycles does it take for your state machine to run or anything like that. But if you really cared and you wanted to do stuff fast, you'd be like looking in your head to overlap stuff every chance you could get. Okay, and if you had to wait 10 cycles to get something out of the memory, you'd say, well, what can I do other stuff while I'm waiting? Okay, can I overlap the next one? Okay, some things like if you drop like a divider down in your FPGA, okay, it may take 50 cycles. You put 2 integers in, it takes 50 cycles for the number to come up. But you can provide new inputs every cycle. So you can have like 50 divisions going on at the same time in the hardware. Okay, so this is quite common in hardware to be able to pipeline things and overlap them. Okay. So let's see, I'll put this back down. Or on that side. Okay. So, and look, it even says, yes, I pipelined this loop for you. Okay. It also makes a guess at how many resources it's going to take. Okay. We had 1,000 numbers, and it says, okay, I will use 2 VRAMs to store those numbers, and I'm going to need 48 flip-flops and 169 LUTs, okay, to do this module here. Okay. We can go look at the Verilog. Let's go look at it. Let's look at it in VS Code. Yeah. Let's go look at it in VS Code. So it gets put in this implementation folder, and it actually makes Verilog and VHDL for us. It just says, hey, maybe you have a favorite, and we like looking at Verilog, okay, but it makes them both. Yes. Okay. So here's the Verilog it made. Okay. It's actually not bad. I've used other tools that generate about like 5,000 lines. So, okay. So let's see what we've got here. We have a clock signal and a reset signal. Okay, that's not too surprising. But we probably want to like control this thing in some way. So we have this start signal that's an input. So we can tell it when to go. And it feeds out a done signal when it's done. Okay. And there's actually like there's actually a couple more that come out idle and ready. We are pipelining the loop inside of this module, but you could actually pipeline the module as a whole. So if you were like providing inputs, you could provide new inputs while it was still working on your old inputs. Okay, so that's kind of this ready signal says, well, I may not be done yet, I may still be working, but I'm ready for new inputs to overlap things. Okay, but in the end, we have an input signal and we have a return value. Okay, and these are just these are just ports. Okay, and let's see this beautiful Verilog that we've written. Okay, so I don't know, does this look familiar? Hey, you've got a current state register. Okay, sorry, I know most of your system Verilog you used to logic, but in Verilog we use reg or wire. It doesn't really matter. Okay, so then, hey, look, you've written code like this. Okay, if I reset it, go back to state 1. Otherwise, current state equals next state. Okay. Okay, and then next block. Next block. I don't know what all these things do. Okay, so basically this is a flip-flop. Okay, and okay, this is an always FF block. Okay, and it basically says under these conditions, put this data into the flip-flop, right? So somewhere we must have like an add 1, maybe. We had like a plus, I don't know. Here's our next state block. There you go. Here's our add 1. Okay, and some other stuff, I don't know. It's not really meant to be read by humans. Okay. But it works in the end. Unless it actually has a submodule, like has the memory. Just do it. Okay. So this is like the memory is actually modeled in Verilog as well. Okay, it's a ROM in this case with like an address signal, an enable signal, and a data coming out. Okay, so let's dig. Oh no, sorry. And then there's like this DAT file. Yeah, this is what gets put in our memory. Okay, which was my array. Okay, so that's good, but 1,000 cycles isn't good enough. I want it faster. I don't want to wait 1,000 cycles for the answer. Okay, so all right, let's. How would you make it faster? So I know you're not HLS experts, but you are Verilog experts. Well, okay, maybe not experts, but you could write some Verilog code. Okay. So, all right, we said we could do it in 2,000 cycles. I showed you this cool way we could do it in 1,000. Okay, now make it faster. How are you gonna make it faster? Don't worry about HLS or anything. Just we gotta look through this memory, and we gotta see how many of a certain number in there. How could you do that faster? Yeah.
More than one.
Okay. Okay. So yeah, I mean, we could. So yeah, I mean, we could. Let's just make it go twice as fast. We could do this, right? So now every time we go through the loop, we're getting 2 things out of memory. And okay, so that's good. And we're jumping by 2, so we only have to do the loop 500 times now. So okay, what could I keep doing that? This is called unrolling a loop. Okay, so I could unroll it again by a factor of 4, okay, I could get I plus 1, I plus 2, and I plus 3 out and skip by 4s. Let's just assume that my thing remains divisible by the number so that it's nice. If it's not, things fall apart fast. Okay, so, okay, I could unroll it by 4, 8, 16. Yep.
As you're doing that unrolling, I'm not sure if this is going to be an issue or not. We may want to have separate variables counter occurrences, and you just add them together by default.
Okay.
I don't know if that would help in this case or not. But
Okay.
it doesn't have to be another iteration of adding to the same thing.
Yeah, you're worried we're trying to touch the variable twice, like at the same time.
So it might have some blocking or ways to do it after the
Okay.
comparison. I'm not sure if that's going to be the case.
Sure, but we could, like, you could say we could have 4 different variable sums that we were keeping, and then at the end we could add them together to kill that dependency. Yeah, that's good. Okay. So what else? Can I just unroll it? Could I do all 1,000 in the same cycle? Maybe.
Depends how much your hardworking use can make it.
Ah, okay. So these are the problems of hardware design that we don't really like get into in 220, but we talked about things being like compute bound or memory bound. This is not a compute bound application. The computation is like pretty boring. It is memory bound. We can run this thing as fast as we can get data out of memory. How fast can we get data out of memory if we put all of this in one memory? Okay, let's pretend the bus is infinitely fast. How fast can we get stuff out of memory? We talked about how we get it out of memory, right? The memory is not this magic block that just has an output for every single entry in the memory, right? We have to provide an address, and then the data comes out. So how many things can we get out of memory each cycle? Just one, unfortunately. Okay, so our whole approach is kind of killed. Okay. What was that?
So what if it's like it has 2 address inputs?
Ah, what if it has 2 address inputs? Okay. So yes, the memories that, come on, pen. Okay, well, I guess I'm not drawing a picture. Is my pen dead? It would appear so. Okay, so yes, some memories, like the BRAMs on your FPGA, are called dual-ported memories. They have 2 sets of these signals, 2 address, 2 read, 2 write. So you could read 2 things at once, or you could write 2 things at once, or you could read 1 thing and write another thing. Okay, so I'm going to undo this, these changes we made here, and I'm going to go back here. And you know what? We don't actually have to modify our code. We can just tell it to do it for us. So I'm going to go over to this array, oops, the loop, and I'm just going to say, hey, insert a directive, and I'm going to tell the tool, please, what do we call this? Unroll. Please unroll this by a factor of 2. Okay. So let's do it. I'll wait 30 seconds again. And you have a USB-C charger here? You do? Okay, well, I don't need it yet, but if we get to that point. It's like 2 years old now, so the battery's not what it was. Oh, 155. I was pretty close with my 160 guess. Okay, so, all right, how fast does it run now? So the loop takes 500 cycles now. Okay, so we did it twice as fast. Okay, so let's crank it up. So based on our previous discussion, what do you think of the idea of changing the unrolling to a 4?
the word size?
It's a 32-bit, which is the same as our array. Yeah, you're right. If your memory was like smaller things, you could like, if it didn't do it for you, you could like cast the pointer and get more things out and mask them and stuff. Yeah. Okay. Yeah. Yeah. Okay. So what do you think? Down to 250 now or not? No. No. Okay. Let's see. Come on, 250. It's working harder. It literally is taking longer. Oh man, violation. Okay, so yeah, the trip count, okay, it knows it only has to go through the loop 250 times, but we haven't actually made it any faster. Okay. So, and in fact, we can go look at kind of a visualization of how we call this scheduling, how it assigns all these operations to clock cycles. Yeah, so these are essentially, it compiles it down to assembly like code, and then it maps those to different states in the state machine. So what you'll see here is that this is basically one iteration of the loop. There's a read operation and a read operation, and you'll see those both happen at the same time. Okay, but the next ones don't happen until the next cycle. Okay, so it can do 2 at once, but it can't do 4 at once. Okay. All right. So your manager says, too bad, make it faster. So how are you going to make it faster now? 3 won't, yeah. 3 won't divide into 1,000. It'll just make it even worse, actually. It'll be slower than 2. Because you'll have to do some extra checking at the end to do weird stuff. So, okay. You can only get 2 things out of a memory at the same time. How can you make it faster? Make more memories. Okay, good. Okay. So you can't always just make more memories. It depends what's putting this stuff into the memory. Something, usually you don't have like hard-coded values, but if it really is just like a ROM like this, a lookup table, and you need to check how often something's in a lookup table, yeah, you could split it into different memories, okay? So I could split it into different memories manually, but again, that's horrible. So I'm going to tell it to do that for me, okay? So if I go back to this view, to my, come on, where's my little thing over here? There we go. Okay. So I'm going to go to this memory, and I'm going to insert another directive. Now this tool is a lot more powerful than we're talking about. You'll see here there's lots of different directives for everything we select. Like the loop had way more than this, but okay. We're going to, what do we do? Array partition? Yeah. Okay. So this is a single dimension array, so we're going to be partitioning dimension 1. And then a factor. How many do you want to split this into? How many memories do you want to split it into?
How many memories are available?
On this part? I don't know. How many memories are on this? On like a 35T? Or this is a 20, this is the thing of 35. 20, I don't know, like 50? 50 or so memories? Let's split into 10. Should we just go with 10? Okay. 40. Okay. So now we have to choose something else. You can imagine if I'm taking 1,000 entries in the memory and splitting it, do I want to split it so that, okay, I'm splitting it into 10 memories. Do I want to put the first 100 in one memory and then the next 100 in the next and the next 100 in the next? Or do I want to put in 0, 10, 20, 30 into one memory and 1, 11, 21 into the second memory? Does that make sense? Okay, so that this is block and cyclic. Okay. So what do I want to do for this algorithm? Block. So block says the first 100 elements are going to go in one memory. Is that going to help us?
If you're rolling, you probably want the cycles, where it's like every 10 one is in a different.
Yeah, because the first iteration of the loop, we're going to read from I plus 1, I plus 2, I plus 3, I plus 4, all the way up to I plus 9. And we want those to be in all different memories, right? Not the same memory. So we want cyclic. Okay. Okay, so now we've split the memories. That's not going to make it faster until we actually unroll it. So what unrolling factor do you want to use to fully saturate our memory bandwidth? 20? Good number. Okay, now this might actually take a little bit more time. Maybe it'll take 2 minutes instead of 1. Okay, how fast is it going to be? 1,000 divided by 20. 50? That's pretty good, right? From 1,000 cycles down to 50 cycles. I promise you your software would take far more than 50 cycles to do this. But we're going to use up like half the VRAMs on the chip. So 140. Oh, we could have really pushed this. Okay. What have we done? What happened? What did we screw up? Oh, okay. I remember now. Okay, so the tool's not perfect. And it doesn't like that we have this if statement. And what happens is a little bit what you were talking about, where the if statement kind of confuses the tool a little bit, and it says, well, you might be doing one thing to this variable, or you might be doing another thing depending on which branch you go down. And so now if you try and do this all at the same time, well, I need to basically I need to resolve this branch before I can deal with the next one and the next one. If you imagine this is all unrolled, okay? So you'd think the tool would be smart enough, but we're just gonna get rid of the if statement. Okay? How can you rewrite that code to get rid of the if statement? I just want to remove the word if and else. What could I do? Okay. Okay, that one I know works. So, but it's probably right. So we're gonna say, sorry, let's see. We're gonna say if this is true, then what? So, these tools aren't like the most mature tools. So, you think it should just do this for us, but it doesn't. So, and if you dug in a little bit, you would see what was going on, and you'd see that this is the problem. In fact, I should have gone back. This violation, we could have clicked on, and it would have kind of pointed us at this and told us that we have some dependencies on this variable. Okay, so what are we seeing now? 50? It was really fast last time because it didn't actually have to do that much work. Hey, we did it. Okay, so 53 cycles to do this loop. Okay. So there's lots of things you can do, but generally the best performance you get is some combination of pipelining and unrolling and splitting up your data with partitioning such that hopefully you saw that really the goal through all of this was to take some C code that does not describe any parallelism and try and make parallelism happen to an extreme, right? So essentially now every clock cycle we are getting 20 things out of memory. And think we need a lot more adders now, right? We have to do all of those additions. Let's go look at this thing. Okay, if I expand this, okay. Yeah. Okay, so now I've got like all these additions happening going on, all this stuff, and you should see now we're at 755 lux. Do you remember what we were at before? 52? 149? Okay. Yeah, so we paid for this performance. Okay. So it's a trade-off. We could make, this is the other cool thing about HLS, is by changing these different options, we could make lots of different designs. Okay, we could make some that are very slow and use very little resources, or we could use some that are very fast and use a lot, or we could do everything in between. Okay, so I'm going to take this to the extreme. We're going to do it further. We don't have enough memories, but let's try it. We are going to... How big are the VRAMs? Pretty big. How big are they? What am I looking? Oh, window. I want my directive. Okay. So I'm going to partition this differently. I'm going to use the not block or cyclic complete, which says put all 1,000 numbers in their own memory. We don't have enough memories for that, but that's okay. What other memories do we have? What was that? Yeah, right. Flip-flops are really just like a shallow memory. It stores, right, one thing, or we group them together. Let's say a 32-bit register. Okay, but we can get it out. We can get the data out any cycle, right? So if we do this complete, we're essentially going to use 32,000 flip-flops. Okay, but we've got 32,000 flip-flops, so that's okay. And so I don't know. Let's unroll this thing more. 1,000? No, I'm gonna get scared. It's too much. It's gonna break something. Okay. So yeah, I mean, flip-flops are kind of memory, right? And that's kind of one thing that's neat. Another way to think about them is, I mean, across your FPGA, okay, your FPGA may be slow. It may only run at 100 megahertz, and your i7 and your machine is running at like 5 gigahertz, okay? But your FPGA has a ridiculous amount of memory bandwidth across the VRAMs, okay? What, 150 VRAMs? Yeah. Okay, so that means you can get, right, like 150 words out of memory every cycle if you wanted to. No, 300, right? They're dual ported, okay? So you can get a lot of data out if you kind of make use of all these VRAMs. And plus you have all these registers. If you start using them like memories, you can get stuff out even more. See, it's going to take a little while. So, okay, so we're almost done. We're going to talk about one other thing while this is running. Okay, our Verilog's a little bigger now, I imagine. So it has to deal with all the unrolling and junk. I don't know. Yeah. There's all this stuff now. Okay. But still, at the end of the day, there's just a state machine with, oh, we didn't go look at the states. Aren't the states somewhere? Oh, cool. We got 3 states. Okay. So, yeah, there's no enums in Verilog, only system Verilog, so we use parameters. Okay. So this is nice. We have wires coming in and out. That's what we've done in 220. What did we look at the hardware modules we looked at on Monday? How did we interface with them from the processor? It was the GPIO block, but how did we talk to it? It wasn't, the processor didn't like set a wire to a value. Yeah, it's through AXI bus. There's a lot of signals, but a bus. It basically allowed us to, it had registers, right? Like in 330, there was a register space. It had, you know, at address 0, the space address plus 0 is the data register. And the base address plus 4 is the tri-state register. And the way the processor talked to it was not by just like setting these hardware wires, but through this whole bus protocol where it could read and write to different registers. So we would like the same thing for our module, okay? We would like the processor to be able to start it. A one-wire start signal doesn't cut it. We would like a start bit in a control register, okay? That's normally how we talk to stuff from hardware. So you could make some Verilog wrapper that has some bus logic that then feeds the stuff into this, but again, the tool will do it for you. So let's go see if it's done. Okay, it's done. Woo, 13. Okay, so, okay, but you see, there's kind of diminishing returns. These kind of couple cycles of overhead start to actually matter now. You didn't really care about them when it was 1,000, but now it's like 1,000 watts. Yeah, that's not much. Is the flip-flop like, it's really only 170? Oh, okay, I lied. The LUTs can also act as memories, okay? So they're called LUT RAMs. And so it's not using the flip-flops as memories. The LUTs are a little bit denser. It's using 9,000 LUT RAMs instead of like 32,000 flip-flops. Okay?
Do those tools like generate kind of like caching logic and stuff like that, or do you have to put that in your code?
Okay, so caching logic, you'll notice we're going to quickly run out of space. Okay, this is nice. I can make this huge looking array with 1,000 entries, but you'll notice, I mean, that's not that much, right? Real big data would have perhaps millions or megabytes, and we don't have actually much VRAM space. So what we would like is we would really like to store data in main memory in the gigabytes of DRAM we have. Okay, it's slower to retrieve it and fetch it, and we need to do it through a bus to do that. And so we're going to do that in a second here. But then, yeah, you kind of could. You could make. You'd have to do it yourself, but you could make some things that copy from main memory into like a local array, and then you do stuff in your local array, and you copy them back and stuff like that. This is a lot of being a good hardware designer, and not just someone that can write some Verilog, but if you think about how to design the system, is what sort of memory hierarchy you're going to use. Where's your data going to live? How are you going to move data around efficiently? Are you going to store it places temporarily and VRAMs and stuff like that? Okay, so again, that's not what this is about, but if we taught like a 320 after your 220, we don't. You have to wait till take 620. So okay, so we're almost done. We want to make a bus. Okay, so we're going to go into here. And okay, I'd like to control my whole function through a bus. So I'm going to go up to the function, and I'm going to say interface through an AXI light interface. Okay. And now I'm going to delete this unrolling just and this partitioning just so that we run a little bit faster here. Okay. And I'm going to run the C synthesis. And when it's done, what I could run here, this next drop down, there's an export RTL. It'll actually take this and package it up and create an IP that you can drop into your block design in Bravado and wire it up to the bus just like we wired up the GPIO on Monday. Okay. So again, you can build a whole hardware system without writing like a line of Verilog. Okay. So yeah, we're gonna let this finish, then we're gonna look at, okay. You'll notice the LUTs are 222, even though I went back to like the basic design. We're paying some overhead for this bus logic. Okay. And so now if I go look at this thing, okay, it's got all these axis control signals, okay. And in fact, if I go, let's see, last thing I want to do is let's see, sorry. It has these axis control signals. You'll see the like start, done stuff is just gone now, okay. Still the input is here, okay. I would like the input, I'd like to provide the input value through the bus as well. Okay, so I can go to input and insert directive, interface, axis light. There's lots of different ways you can provide data in. Okay, and I'm going to generate that again. Okay, and so then what we're going to do here, let's go expand this implementation. We're not quite there yet. Wait for this to finish. Come on. Okay, so then I'm going to basically make an IP for it. And it's going to package it up as an IP. And what's really cool, what we saw like with the GPIO IP, is it had a built-in software driver to talk to it, right? We never to talk to this GPIO, we never had to actually do like register read and writes like you do in 330. They just had a driver that did that for you. So same thing happens here. It will make a driver for us for this custom hardware. I'm looking for it there. Oh, no. There we go, IP. So if you look in here, drivers, let's go look in VS Code. It actually makes a driver that works in Linux and bare metal. It's pretty fancy. Okay, so it makes a few files for this driver. One, this is Xilinx convention, this _HW. This is like the low-level hardware interface. And there's no PDF document that Xilinx produces for this hardware that tells you the register map because you just made this hardware, okay? So this is the PDF document they print out for you. It says, hey, here's your register map I made for you, okay? Register 0 is the control register. Bit 0 is the start signal. Done, okay? You have some interrupt stuff. Down here, offset 10 is the return value, and offset 18 is the input signal, okay? So if you wanted to call this thing, you could make a driver that you'd write to this register your input value, then you'd write the start bit, and then you'd check the done bit till it was done, or you'd check the interrupt output, okay? And it makes nice little things, but it has a driver for that as well. So, so you'll see there's just nice helper functions for start, is done, is ready, get return value, set input. Okay, it writes the register, it takes care of this stuff. Okay, and yes, there's even like a Linux one that deals with the device tree and UIO stuff as well. Here, so you can do it in bare metal or Linux. So the last part, I think I won't show you, but okay, so this data is here. What if I didn't want the data to live inside the function? What if I wanted it to be out in main memory? Okay, out in the DDR chip. That's very different. Okay, so what I could do instead is I might make something like this. Okay, and kind of just wipe that whole thing away and just have a pointer here. Okay. Now, when you have a pointer, you can have special kinds of interfaces. Okay. This is no longer just one value we're putting in. This is like a window into the whole memory system where we can go and get things out. Okay. So just having a register, a memory register, doesn't cut it here, right? We would like to use this pointer to go out to any address and get data. Okay. So, right, this model here of using a pointer in C, we could use that for random access memory. So basically, I want to get data from any address. Okay. And to do that, we would insert a directive and we'd say, we're going to make a master on the bus. Okay. So now we saw kind of a bus connection where the CPU was controlling things and it was controlling our GPIO or our accelerator. Here we would make this be the boss, and it would essentially go into the processing system, and it would be allowed to initiate its own read and write operations to get data out. Well, it becomes its own DMA, essentially. It builds the hardware that can talk to the bus and get data out of memory. Okay, so you wouldn't need a DMA. You could do other things. You could make a streaming thing. Maybe you have some circuit that just provides this whole array in, not through a memory access bus, but through like a FIFO, okay, or just like a stream of data coming in one cycle after the next. So you could apply that directive, and you can say, oh, this is just like a streaming in, and then basically what will happen is every time you dereference the pointer, it will, like, depending on what hardware you tell it it's hooking up to, you might say, oh, this is hooking up to a FIFO. It will just know the signals to a FIFO, which is basically get the next thing at the front of the list. And it will build the hardware depending on how you ask. So it's quite powerful that way. But the main memory is much slower than the DRAMs on the FPGA. I don't know, Hayden, do you remember when you moved your, wasn't this application, but when you moved out to main memory, how much slower was it? 10 or 100 times or something, like, yeah, 10 times slower. And you can't do any unrolling at that point. There's no, like, there's just one DRAM. You don't get to, like, unroll it and say, oh, we're going to split this across like 10 or 50 VRAMs. No, too bad. You get the access to main memory just like the processor does, and so it slows down a lot. So you might do these things where you have a big set of data in main memory and you copy some of it in and work on it quickly and things. It totally depends on your algorithm, how you choose to design all of that. So yeah, I don't know, that's kind of all I have. If you take 427, what we're going to do this year is we're going to, what we always do in 427 is we make Space Invaders running on the pink board that I had here last time. Okay, and generally it's out over HDMI. There's kind of like a buffer in memory that controls what's drawn on the screen. Okay, and so generally drawing stuff on the screen is pretty slow because the processor says, oh, go to this address, draw a red pixel. Now go to this address, draw a black pixel, and it's all going through the processor. So what we're going to do new this year, we're going to have one more lab where through HLS, we're going to basically make something that can draw objects in memory. And so it's going to, I mean, our code was really dumb. It just counted things in memory, but this would just be like, oh, loop through some memory locations and draw an alien or something like that. Yeah. Yeah, so yeah, it'll be much faster, but even if it wasn't that much faster, if you were really cared about it, your processor could do other things while this is going on, remember, right? So you could start it off, you could go do something else, and then you could come back and check the done signal. Okay, that's kind of what's nice about these hardware, software, these complex heterogeneous systems, is we can just naturally be doing two things at once, just by the fact that we're running software and hardware. So that gives us opportunity to speed things up that way. So that's it. I don't know if you have questions or anything before we take off. people usually ask me, should I have just done could I have done my 220 labs using this instead? I don't know. It would have taken you longer to learn probably, but I don't know if the Verilog meets the 220 coding standard, but it would be kind of funny if you submitted this and they looked at it and they scrolled through it and they're like, what is this? You're like, it works, don't worry. But okay. Well, thanks for coming.